Hello.
Yeah, hello. I think it should be audible now. Can you hear me?
Yeah, I can hear you.
Yeah, that's great.
How are you?
Oh yeah, I'm just not doing great because I got sick. So I think I will like spend most of the meeting in the background because most of the time I'm sneezing and I don't want to broadcast sneezing.
Sounds good. Hope you feel better soon. Hi, Zidesh.
I'm just gonna try and share my screen. And can you let me know if you are able to like read what's on it?
Sure. That looks good.
Looks good. Okay. I'll just start sharing once we start.
Perfect. Yeah, usually we start like maybe a few minutes after 5. Just a few minutes more until like people slowly join. How are you doing?
I'm good. How are you? Waiting
Pretty
for
good.
Good morning, Stash. Good morning.
Hey, Andy.
Yeah. Lindra, right? Your name?
Leandro, yeah.
Leandro. Are you from France?
No, I'm Swiss.
Oh, Swiss, okay. Not far away?
Sorry?
Not far.
Where are you?
Oh, I'm in USA.
Oh, okay. Yeah, that's a little bit further.
I mean, you are not far from France. That's what I'm saying. Okay, I'm not saying you.
Yeah. Yeah, that's true. I'm going to Paris next week. It's only like 4 hours away by train.
But I think Switzerland had like French or German, different, region.
Yeah, exactly. In fact, also Italian.
Oh, really?
It's
Wow,
only a small piece, but yeah, there's like an Italian part.
Oh, nice to hear. Nice to learn. Yeah.
With almost Italian climate, which is nice. So it's always a little bit warmer there.
Nice. I saw you answered a lot of questions. Really appreciate it. It's helping us to understand.
Yeah, we're trying to do our best. Sometimes Discord is a little bit overwhelming.
I really love the book from the perspective of combining theory and coding, so you can see how the theory is implemented in the coding. I mean, it's not that theoretical, so it's not intimidating. So most people with some programming experience can, solve. It's really nice.
Glad to hear it. Yeah, that was the goal, because we thought like most people that want to actually use these things, they need to code. So it makes sense to explain it in code rather than just in theory, because then you essentially just serve academics.
Yeah,
And
I mean, yeah, some books looks like a mathematical book. It's so much matrix manipulation, and I mean, it sounds like intimidating for some people. But this, I mean, it's not necessarily that way, right? It's because everything is already wrapped up in the library. You really don't need to know too much of that detail.
Indeed. Cool. Let's see. I think we can get started. So welcome everyone to like the third session of the reading group. Today we're gonna do again like two parts. The first part focusing on the book. Sidesh agreed to give a quick presentation on the anatomy chapter, and then we'll have some time to discuss things that are in there. That can be pretty much an open discussion. And then at the end, I'm gonna show a little bit again, like the open source side. So last time BB gave a nice introduction how to contribute and how to open a PR on an open source project. And I thought today it makes sense to maybe give a little bit more deep dive into like how you actually do it when you have to run tests and what the CI does of a repository, to see like the whole end-to-end thing. Cool. I think with that, I hand over to you, Sidesh, so you can give us an introduction to transformers and the anatomy of transformers.
Yeah, sounds good. Yeah, if anyone's not able to read what's on my on the screen that I've shared, please let me know. But hey, my name is Satish. I'm a machine learning engineer at Cash App. So yeah, let's dive right into this. So today we'll be talking about the transformer, the third chapter, which talks about the transformer's anatomy, and we'll go over the building blocks of what goes into the encoder and decoder stack of transformers, and simultaneously look at the code for it, which is largely just copied from the book. So the first component is the scale dot product attention. In the scale dot product attention, we have three inputs: the query, key, and the value vectors. We compute a pairwise dot product for every pairs in the query, for the query and the key vectors. The scale part of it comes from scaling the attention scores, which is basically the output of this matrix multiplication by the square root of t. The original authors of the paper basically explain why you divide by square root of t, and it's under a limited assumption on the vectors. So basically you divide by square root of t because you want to make sure that the variance of the dot product is in check. And you can read about that in the original attention papers. I'm not totally convinced by that argument because it makes a very limited assumption on the queries and the keys vector. But anyways, moving on to the next part, which is an optional mask, which we'll go over in the decoder part. But to start off with, you can ignore this. The output of the attention weights is then passed through a softmax to normalize the values between 0 and 1, and those are then multiplied by the value vectors, which gives a weighted, which gives a linear, which gives a weighted average of the value vectors. So moving to the code, like I said, there are three inputs: the query key and value, and mask, which we are ignoring for now. The shape of the query key and the value vectors are of batch size, the number of tokens in the sentence, and the embedding size. Torch, the batch matrix multiplication in Torch will then take the query, and then we transpose the number of tokens and embedding size dimensions of the key vectors. And as a result, you get a tensor, which is of shape batch size by number of tokens by number of tokens, which is what we want. Next is the scaling part, where you divide by the square root of the embedding dimension. And then you normalize using softmax along the dimension, along the row dimension. And this is just a statement to basically check whether those attention, the softmax, the attention weights, the sum of the attention weights is 1 along the rows. And then you return another matrix multiplication where the representation for a value vector is a weighted sum of the other value vectors. So one question I had in my mind is, why not use the embeddings as queries, keys, and values? The embeddings themselves as the queries, keys, and values in the book. In the original transformer architecture, there is a linear transformation that is applied to the query, key, and the value vectors. And this is addressed in the book as well. But if you assume that the norm of the embedding vectors is 1, the maximum dot product that you can achieve is 1, and that is achieved by the same vector. So if you use the query, key, and the value vectors as is, so all of them being the same, you would have ones along the diagonal of the attention scores matrix. And as a result, which would be the maximum value for along every row as well. And as a result, softmax will assign the highest weight to the same vector. And as a result, the embedding, the value vector would be a weighted sum of all the value vectors, but the highest weight would always be assigned to the vector representation of the word itself. And as a result, you would not be taking into consideration the context, which is the entire point of using attention. Next is the multi-head attention. So in multi-head attention, we basically use the same attention layer that we spoke about now, and replicate it 3 or 4 or 5 times. In the book, in the original paper, I believe it's 8. And the reason behind, sorry?
Just quickly, somebody in the chat mentioned that if you could make the font in the editor a little bit bigger, that might be helpful.
Is this good enough?
Yeah.
Sorry, I can't see the chat. Okay. Right. Thanks. So in multi-head attention, you have multiple attention heads. And in order to make sure that the output dimensional, the embedding size of the output of the multi-head attention is the same as the input, each attention head will operate on a smaller subset, on a smaller dimension of the original embedding dimension. So you need to make sure that the per head dimension, the embedding dimension is a multiple of the number of heads, is an integer multiple of the number of heads. I thought this was a good point to call out a blog called The Illustrated Transformer by Jay Alamar. I don't know if people have heard about it, but it's a really great blog, and it was my first introduction to transformers. And in the blog, he's a little, his section heading for multi-head attention is really dramatic. He calls it a beast with many heads. So I just passed that text prompt through Stable Diffusion to generate this image. Just a small aside. The next component of the encoder layer is the feed forward layer, which is a simple 2-layer feed forward network, which uses the Gelu nonlinearity. And it is called a position-wise feed-forward network, or 1D convolution, because the same matrix, the same MLP is applied to each token in the sentence. And finally, to put it all together, there are there is layer norm and skip connections. These both are utilized to basically aid training and make training faster. Layer norm normalizes the mean and the variance to 0 and 1 for each token embedding. And skip connections basically deals with the vanishing gradient problem. So putting it all together, the transformer encoder layer contains multi-head attention, 2 layer norms, and a feed-forward network. And in the forward pass, to implement the skip connections, we add the same input to the attention layer to the output of the attention layer. Similarly, another skip connection where the output of the layer norm, so this output is added to the output of the feed-forward network, which is what this X is. And finally, we return layer norm, the layer normed output of this part. So that's all that's there in the encoder of the transformer. The decoder is largely the same with some minor, oh, I skipped positional embedding. So, so one part that I skipped over that I don't have in code here is the positional embeddings that are added to each token in the transformer. Since the transformer by its structure does not take into consideration, does not have any sense of time, since you're just doing a linear combination, of the value vectors, you need to add some sense of the position of the tokens when you pass that as an input to the transformer model. That's where the positional embeddings come into play. In the book, the positional embeddings are learned, but in the original transformer paper, they use this cosine, they use some combination of sine and cosine waves to get a positional embedding, which is what is illustrated in this image, where the y-axis is the token position. So each row corresponds to the embedding that would be added to the token at position 0, position 1, so on and so forth. And the embedding dimension is the vector for each position embedding. And then moving on to masked self-attention. So similar to what we saw, similar to this dot product attention, we just need to make a minor modification to add a mask, which is basically used to remove the attention of, so it is used in order to not take into consideration certain part of a token when computing the embedding for it. In the decoder for, in the transformers decoder, you need to mask the tokens to the right of a word for which you are making a prediction. Since if you don't do that, the decoder will basically learn to just copy that output, copy that word, copy the next word in the sentence to the output, and that is not what we want. So just to and how So let's maybe quickly go over what the scale.product attention looks like. So we get the attention scores as usual, we normalize them, and then we apply a mask. So the values which we want to mask are set to negative infinity, since once you apply a softmax to them, those scores will become 0. And just to quickly look at that, before the attention score, so I'm printing the attention scores before applying the mask. There are some random values. After applying the mask, the off-diagonal elements in the upper triangular part of the matrix will be negative infinity. And then after applying the softmax, the attention weights in the same position where there's negative infinity become 0. Next is the encoder-decoder attention, which is again very similar to the encoder attention layer that we saw, except for that it takes the key and the value vectors from the output of the encoder. And putting it all together, the transformer decoder layer contains multi-head attention, the encoder decoder with masked multi-head attention. So we pass an argument for the mask, the encoder decoder attention layer, the feed forward network, and 3 layer norms. So 1, 2, and 3. And yeah, similar to how this was implemented in the encoder, we have some skip connections. Yeah, and the encoder decode, and the only change in the function signature is that you accept the key and the value vectors from the encoder to compute the encoder decoder attention. And that's it. Does anyone have any questions?
So Siddhesh, you did some work by yourself on top of the original notebook from the book, right?
Right. I haven't looked at the notebook from the book, but the encoder decoder attention part was not implemented, I think.
Yeah, I think we skipped that because the chapter was already too long. We were told we can't spend like half the book on theory. But I think your implementation is pretty clean.
Good, good.
Yeah, I think also on Discord somebody had a question this week, I think, about like how the data is fed to a decoder, like is it fed sequentially and so on. And I think that plays into what you've been showing with the mask attention, where you can see that you have to mask certain parts of the decoder inputs. So the decoder essentially gets, during training, it gets like the target sequence as input, but all the words, the current word and the future words of the sequence that the decoder has to predict, they're masked out, so it doesn't have access kind of like to the future and to the current token. That's the goal of the mask attention.
That's
Are there other questions?
That's
Yeah.
for architecture like GPT, right? Like it's but for BERT, it's like you do both sides, right?
Yeah, exactly. So essentially, there are like 3 families of models. There's the encoder models like BERT, there's the decoder models like GPT, and then there's the combination of both, which is actually what the original transformer was, which has an encoder and decoder. And the masking of the attention happens both for encoder decoder models and also for decoder only models like GPT. An example of an encoder decoder model is, for example, T5. Are there other questions?
So the parallel processing of the token, like each batch, I remember the batch size maximum is 512, something like that. The parallel processing, that's a big advantage over the previous like RNN, architecture. I'm seeing how it's implemented. Like we do have some, implementation in the notebook, like a BMM, and I think that's nice. I'm pondering on this, how this parallel thing is implemented. Like BMM, it's kind of a parallel computation, right? I googled a little bit. I saw the API. I didn't spend enough time on it. Maybe I think that's where the parallel processing is from, or maybe I don't know. So actual implementation is looking like this, or it's only in this book.
No, that's actually the implementation. I mean, we don't implement like the exact transformer implementation, how it's done, for example, in Hugging Face, because there's a lot of like code around it to make it work with the hub and so on. But like the gist of it is like pretty much the same thing. The main reason why you can parallelize the transformer much better than, let's say, an LSTM is, for example, if you have an LSTM, what you need to do, you pass in like inputs sequentially, and at the very end, you need, for all the inputs, you need to kind of unroll the LSTM. Each pass of the LSTM you need to unroll. So if you have a very long dependent, let's say, graph, and you need to backpropagate gradients through there, and you need to unroll it like essentially at once. And in the transformer, right, like all the computations are very independent from each other. So you can compute each head, attention head, independent of each other. In the feed forward, the same thing, right? You can apply it independently. Then if you do things, if you train a model that's only like an encoder, for example, you have even more advantage, because processing a whole sequence takes only one pass through the whole model, because you can pass all the inputs at the same time and you get all the outputs. And during training, it's the same thing for the decoder too. So you can pass like a lot of data, and you don't need to do like feed the information back into itself. So that makes the training and inference very efficient. At the same time, currently there is like a limitation, which is the context size. So attention is expensive in terms of how many tokens you have. Siddhesh showed that you essentially get a square matrix, right? And the square matrix is number of tokens times number of tokens. And so if you have 1,000 tokens, then that gives you a matrix with 1 million entries. And if you have like 10,000 tokens, you have a matrix with 100 million entries. So that doesn't scale very well. And currently, like one of the biggest complaints people have, or like biggest requests, let's put it that way, that people have, is that can we have a transformer that has longer attention? Because some people want to, like, for example, summarize a document that has thousands of tokens, and that's not super straightforward with transformers, whereas like an architecture like an LSTM doesn't necessarily have that constraint.
Leandro, I have a question.
Yeah, go for it.
So you mentioned that models like these have small context windows, so it's hard to kind of expand to longer sequence sizes. Could you do like a small fix where you window a model over a larger sequence and then do something with the embeddings that are produced by that window? Or does that end up not being as helpful?
Yeah, you can totally do things like that. I think there are some transformer architectures that kind of do something like this. I forgot which ones it is, but they haven't. The architecture that have that intrinsically, I think they haven't survived in a sense that I don't think they've been doing as well as other models. I think Nicholas Broad, who works at Hugging Face, he made like a small library that does that for classification, where essentially you scan through a document, you make predictions for each like chunk, and then you pool everything together and make an overall prediction. So that's totally possible. There are also some models like Longformer, for example, that have like a more efficient attention mechanism. So you can, they have like larger context windows, but they're like notoriously hard to train. So sometimes you need to find like a very specific set of hyperparameters and then it works. And so I think that has been one of the main reasons why they also haven't been like very widely adapted yet.
Cool, thanks for answering.
Sure.
So Leandro, so I think the max batch size is 512, right? And as you mentioned, because it's a quadratic, and so you don't want to leave a huge memory or computation footprint. It's too expensive. So that's one of the maybe shortcoming of this transformer. I believe researchers are working on it. So is this a parameter you can tune it? Like you don't want to go above 512, but you can tune it to make it smaller, or the transformer architecture make it fixed. It's just 512. You cannot change it.
So 512 is not like a universal number. I think 512 it was used for BERT and a few models around it. GPT-2, for example, I think has 1024. Now newer models, they even have like 2000. I think Bloom was trained with 2000 context window. And I think even some models have been trained with 4000, and they've been kind of vanilla ones. So that's definitely something that you can change, but you need to usually to change it during pre-training, which is the expensive part. So once a model is released like BERT, then you have to take what you get. You can always go smaller, but you can't easily go bigger. One thing they used in, for example, pre-training Bloom, which is a model that we've been training at Hugging Face in like a open collaboration, is a cool way to use positional embeddings. That's called alibi embeddings. So Sidesh showed these positional encodings, which are essentially composed of like sine and cosine overlaps. And one shortcoming is if you want to, after pre-training, if you want to go to larger context windows, the model's going to see like patterns that it has never seen before. So that's why it kind of breaks down. But the idea behind alibi embeddings is that you have a mechanism that can extrapolate. So they did some experiments where they went to like larger context windows than they saw during pre-training, and you could see that the model performance didn't degrade. So it's not, I think, 100% clear yet that you gain a lot by doing that if the model really can use it, but at least the model doesn't just completely fail if you input something that has a larger context window. But that doesn't solve the memory issues when you go to larger sequences. So you can still run out of memory, essentially. That's what happens if you pass in something that has too long sequence, then you don't have any memory left. So with the alibi embeddings, you can still do that. So it doesn't solve everything.
Another question about the positional embedding. I have been trying to understand it. I don't see a whole lot of explanation about it. I did see the sine cosine thing you mentioned. I was wondering how this could, I mean, the reason for positional embedding is you want to make sure you do have something about position of each token in the sequence. But if it's repeating like it's sine cosine, you could see some exact the same value for maybe, because the sine cosine, it's a circle. I mean, circle. It's like periodic, right? How could it make it unique? So it's something
I mean, they didn't just go for like vanilla cosine sine, but they chose like a pattern, especially that doesn't repeat. So if you look how they do it, they scale it in a way such that each position has like a unique pattern that you apply. And I think if you go back to like Sid's slides, you can see like each position looks slightly different than all the others.
And I shared a collab notebook which has the implementation for that positional embeddings in the chat as well.
Yeah, now I remember. Yeah, it's a very complicated formula. They raise something to the power of something. Yeah, that makes it unique. Now I remember.
Yeah. Also note that like not all models use like these kind of positional embeddings. For example, GPT uses learned embeddings, so the model has to learn a pattern for itself that depends on the position, and it varies a bit. I don't think like that many models use like the cosine sine pattern anymore. A lot of them use like learned embeddings, learned positional embeddings, or like alibi embeddings. But I think it's a good entry point to understand what the idea is. Cool. Any other questions?
Maybe this is off topic. The multi-modality thing. If you want to elaborate a little bit, I mean, it's off topic. I'm sorry if you feel you don't feel comfortable. You don't have to say anything.
Sure. Anything specific you want to know about like multimodality? Like how you would do it with transformers?
I kind of I don't know enough, but I think they're almost treating image or video like they're treating, they're making them token, like you are making language, word token. I mean, it's mysterious to me now because I have not spent enough time to figure it out. But looks like they are trying to make everything like almost like a large language model. Am I right?
Yeah, there has been some trend in that. I think vision has been one example. Also, like audio has been using transformers a lot because audio is maybe more natural because it's kind of like a sequence. So it makes sense to try to do it the same way. And like wave to vec 2, for example, is like a transformer that has like some pre-processing before for audio. I think in vision, it's a little bit of back and forth. I think transformers were very successful for language with like that sequence approach. So they try to see, can we do the same thing with images? So they essentially made small patches of images and use that kind of as like a token. And that seemed to be working very well. But since then, it's been a little bit back and forth. And like people from the computer vision community came and say like, but actually, if we do it better, we can do the same thing with convolutional neural network. And I think the jury is still out, but I think at least it seems to be kind of competitive. But it also requires like a lot of pre-training.
Nice.
Sure. I think we still have like time for a few more questions if anybody wants to jump in.
I got a weird question for you guys as not a data scientist. I do a lot of OSINT investigation and sorry, I'm like stuttering today. I'm trying to do all this research to find the right tool and I can't. So I'm throwing it out to you guys is, I get confused about what is the difference between machine learning, NLP, AI, I feel like they throw all of that into one basket, and it's not, because when I messed with NLP, I think it was like machine learning, like it was neat because you're breaking down like vocabulary and syntax. And so I'm trying to find something that can do correlative models of data for OSINT investigations. And I'm throwing it out there to you guys, like what can do that in regards to NLP or machine learning? Point me in the right direction, please. Like I'm ready to break a keyboard here.
Can you explain what OSINT is? I don't know what it is.
Sorry. This is I'm so bad with that. Open source intelligence gathering for like CTFs and law enforcement, and I mean everybody uses, even the criminals are using it now to pick their targets. So and I'm trying to find, like, when you're doing, thank you for doing that, by the way. It was you're a good teacher. If I was doing an investigation on something, or due diligence, because investigation is a legal term, and I had all this data, there's nothing that exists, even with all the experts, that can take that data, parse it in, and then make like a correlation. So let's say I was looking up, you look at somebody's social media, right? You're going to get emails, usernames, and that's a manual process right now. You got to sit there and literally make those connections yourself, which is stupid. Like, we have AI, and we have all these tools that, like, Dolly can make pretty pictures. Like, we should be able to make those links without having to do that with a pen and paper.
Okay, I see. I mean, maybe I can start with like your first question, which is like, what's the difference between AI, machine learning, and NLP? And so the way so AI is like a pretty old term. AI is like, I think, originated like in the 50s, and it was like used for anything that looks kind of like smart, but it can even be like a rule-based system. So if you take, for example, Deep Blue, which was like a heuristic on how to play chess, that was kind of like considered AI. Machine learning is like kind of a subset of AI, which is you use statistical models that try to learn from data. That's not something the broad term of AI necessarily needs to do. If you have like a smart rule that does something, that doesn't need to learn anything from data. But machine learning is the goal is to somehow use data to learn something automatically. And then NLP is like kind of like another dimension, which is more about what modality are you looking at. So that could be AI, ML. Maybe a third term, which is deep learning, is like a subset of ML. So AI is the superset of ML, and deep learning is the subset of ML, which is like mostly about large neural networks. In terms of your question, I think like most of these models, they're very specific for a certain task. And I think what you're looking for is like a combination of many tasks, kind of like a whole workflow that you're trying to optimize. And I don't think there are currently many models that are very good at that. I know that companies, for example, like Palantir, they're more like on that domain, trying to like extract a lot of data and find like patterns in there. But I think they actually don't use that much machine learning and use like a lot of good like data engineering to achieve that, combined with a lot of rules. And I think in terms of like data science, like I used to work as a data scientist for quite a while, and usually people want to do something with fancy tools, but usually the right way to look at it is like, what's the right tool to solve an issue? And it can be a combination of like rules with maybe some machine learning models somewhere, but very rarely it makes sense to start with like fancy machine learning to solve like a very concrete use case.
That answered. Right now I'm using the autism tool. It works very well, you see the path. But that being said, it's thank you for that. It just sucks that, because when people ask, how do you make these correlations? I'm like, if you just threw a bag of M&Ms on the floor, I'm going to see a pattern. So it's one of those things that we got all these tools, and like you just kind of solidified for me, there is a need, but nobody's been able to do it. And you may have just answered it for me, is that sometimes when you overcomplicate a process, you make a complicated process. So it's KISS, right? Keep it simple, stupid. So there is no tool that actually exists. But what was the name of that company? Can you put it in the chat, the name of that company you said that was working on something?
Yeah.
Please. Thank you guys.
Sure.
Sorry. I didn't mean to take that, down the next street, but.
No worries. Good. I think that's a good point to make the switch to open source. And I thought what I'm going to show today is very briefly like what the things are, the steps are involved to open a pull request on a repository, but more like on a very practical sense, for going from like cloning a repository or making a fork of a repository, then making some changes, making sure like all the tests still work, and then finally push again, make a pull request. And it's very similar to what Vivi showed, but I thought it makes sense to go a little bit more in like the details of the steps involved. And I think for future sessions, we can do also a little bit of voting and see like what you're actually interested in, or what you find like the most difficult parts are in contributing to like an open source project. So let me start by sharing my screen. Can you see my screen now?
Yep, we can see it.
Cool. Can you see evaluate? That would be the right screen.
Yeah, we can see it.
Awesome. So instead of doing transformers, I thought I'd do evaluate this week because evaluate is a project I'm mostly working on, so I'm a little bit more familiar with it. And I wanted to show you like all the steps involved to open a PR, mainly like setting it up locally, which is like, I think one of the main hurdles. And so the first thing that you usually do is you need to create a fork, because you're not allowed to commit anything to the main repository. So I'm just going to create a fork there. So now I have like the evaluate repository under my username, and I can clone that. And so what I'm going to do, 1 second, I need to find a new terminal. And I'm a little bit bigger. So I have like a folder git. And I'm going to make a directory called, let me see. First delete it. So I'm going to make a folder for that. I'm going into that folder, and now I'm going to clone that repository I have here. So now I see I have evaluate. I'm going in evaluate, and now probably one of the first things that you usually need to do is you need to install the things that evaluate uses. And I'm usually using virtual env, but you could also maybe use Conda or some other library to make virtual environments. That's usually a good idea, because if you install everything globally, you might break other projects that you're working on. And if you create like a virtual environment, you have like a new self-contained thing. And if you install something in there, then it's only going to affect that particular environment and not everything that you have. So to install, what evaluate needs is you usually do like pip install. I mean, some repositories can be different. You usually can find some instructions in the README how to install things, or if there's like a contribute guide. usually shows how you can install things, for example, here. And so if you want to install everything that Evaluate needs, usually what you do, right? If you want to install Evaluate, you do just install Evaluate, and that takes the library from PyPy, which is like the released version. But since we're going to be working on it, we're going to do that -e. That means editable. And then we have a dot, which means you install whatever's in the folder that we're currently in. And then you have that addition of def, which is we don't not only going to install everything that Evaluate needs, but everything that Evaluate needs for development. So when you release a package, you don't always release all the things you need to develop the package. For example, you don't need unit tests, the dependencies of the unit tests as a dependency of your package. So if you do that, that's going to install a lot of things. It's a very long list of libraries. You can see it uses a lot of cache because I did the same thing this afternoon already, but usually when you do it the first time, I see something updated. It needs to download a lot of packages. Now it's installing.
Yeah, Andrew, quick question. I don't see you are doing install evaluate, but it's installed. So that -e is doing the magic or what?
Yeah, so the -e and the dot, if you look at the folder that we're currently in, it has that setup pi. That's from the Evaluate repository, and the setup pi is essentially the recipe to install Evaluate. And if you do -e dot, then that says install whatever folder you're currently in, and then it looks for that setup pi thing.
Okay, so this is universal. I mean, you can use it in other repository, right? To install other package. Okay, thank you.
Yeah, exactly. And you want to do that because maybe you want to test it and you want to test against the local version, not against like the last release or something, because you're going to make changes, right? So you want to make sure if you import Evaluate, it's going to import that folder that we're currently in. So now we installed things. I'm going to quickly uninstall TensorFlow because I'm on a Mac and that usually breaks things with me. You can make it work with Miniconda, but I rarely use TensorFlow, so I'm going to uninstall it for now. But that's just a local thing on my machine. I use VS Code, so I can open VS Code in that folder. And let me put that here. Maybe I can also make that a bit bigger. And now you can see here we're in the source code of Evaluate. Usually the source code is in a folder that's either called source or it has the same name as the package, or like a combination of both. And so here you see like all the code that's inside Evaluate. And I don't know, maybe we just make a stupid change. Let's see, what do we want to do? Maybe we want to import another package because we need that for something. So we're going to do import, for example, NumPy LMP. And you want to probably make a branch for that. And you can do all of that in the terminal, but I'm going to show you what I actually use because I'm very bad at remembering Git commands. So I usually use a tool that's called Git Kraken. You can see it here. And it's like kind of like a visual version of Git. So it's a user interface that you can use. And I go and I select Evaluate. And you can see now, you can see the Git history. That's essentially the Git. I don't know if I can. Oh yeah, I can make that bigger as well. So that's the Git history. So you see all the previous commits that were made. And so what I now want to do is I don't want to commit my change to the main branch. I want to make a new branch and maybe say that's called NumPy. I make that new branch. That's essentially the same, I think, as git checkout -b add NumPy, but I like the visual. And the other nice thing about Git Kraken is you can visually inspect all the files that have changed. So you can see something changed in loading. Let me know if it's too small. I can try to zoom in a little bit more. But essentially, you see the files that have changed and you see what has changed exactly. And that's what I want to commit. So I stage that. That's the same thing as git add. I add a git commit message, which is NumPy NumPy import. We commit. And now you can push to wherever we want. Now, usually before you do that, you want to do 2 extra steps. And I'm going to show you why you want to do 2 extra steps. Every time somebody commits something to evaluate, I'm going to go back to the main repository to show you. Every time somebody creates a pull request, for example, I don't know, we can look at that pull request that I did a couple of days ago. And every time we push something, for most of these repositories, they have a CI, which is essentially tests that run every time somebody adds something. And you can see for evaluate, it's usually 4 tests. It can be much more. One of them is just building the documentation. One is code quality. And the other 2 are running the tests on Linux and Windows. And so one of the most common things that happens is that the check code quality test fails. And that's just essentially a linter. That just makes sure that all the code in the repository has like the same format. For example, you use single quotes or double quotes for certain things. And the check code quality just checks if all of that is in order. And a lot of time people do what I just did. They make the fix, make the change in code, then push it, and then it fails, and then you get frustrated. And probably I could also do a count on my repository, and I think 50% of the time that happens to me too, that I get too excited, I just push, and then figure out, you can actually see it on that PR. I pushed, it failed, and then you see a follow-up commit, which is fix style, which is I forgot to check the code quality. And that's very annoying. And sometimes people get like frustrated with it and maybe even stop working on it because it's so annoying. But actually, like fixing it is like very simple. If it depends in which repositories you are. A lot of repositories use like different things. Yeah. For the Hugging Face ecosystems, we have a command for that, and that's essentially make style and make quality. And that runs the linter, and you can see it actually changed something. Where was it? So one, it complains that NumPy was imported but never used. And I think it also changed some white spaces. And if we go back here, we can see there's now an additional change, which is it changed the ordering because there's some definition of how the import should be ordered, and I placed it in the wrong place. So that would be another candidate for fixed style. And then you commit and push. Now, the second thing that can happen is the code quality is fine, but maybe you broke something else, and the test suite is trying to find if anything broke. If you look in most open source project, there is a folder called tests that has a lot of unit tests that makes sure all the functions do what they're supposed to do. And you can run the tests locally. Also, again, depends a little bit on the repository, usually you find like the exact instructions in the contributing guide. Either you run test, something like that, against like the test folder. Most of the Hugging Face libraries, they also have a command for that, where you can just say make tests, and then it runs the tests with the settings that are also used in the CI on the hub. So that usually takes like a few minutes, but then you can see it spins up. It actually runs the test in parallel, so you can see there are like a lot of workers that are starting, and then it runs through all the tests that are defined in here. And that's much easier to debug than every time pushing to the hub and then waiting for the tests to run. Sometimes they can take a couple of minutes, but with that you can run them locally, and then you see the results. So there's only one step missing. So let's say now the test started, you can see they all pass, which is good. I'm gonna stop it. But oh yeah, let me maybe quickly show. At the end, usually you get like a report that says how many tests passed and which one failed, and then you can look at them specifically to see what happened and what you did that maybe broke something else in the library. If we go back to, I want to go back to my repository. Oops. Oh yeah, here you can see if you, now I'm back in my repository, and you see either you can go to pull requests and just say you want to open a pull request, and we'll show you the branches. Or if you just push something, it usually shows you a message like that where you say compare and pull request. And here you can select where you want to add your change. So either I can go from my branch, which is in my repository, and make a pull request to the main repository, or I can also make it to my own. Depends a little bit what you want to do. Let's go back here. And then what usually makes sense is to write in detail what you did and what the pull request is supposed to do, because somebody has to review that. So the more descriptions you add, the more about your thinking behind like the design of your changes you add here, the easier it is for the reviewer to see if the code that you're having is actually doing what it's supposed to do. And then you create the pull request and then wait for somebody to review it. It helps if you allow edits by the maintainers. That means if you make a, for example, pull request to evaluate, I can also make changes. So I don't need to ask you to make changes, but maybe if it's like something easy and I can just fix it, I can also directly commit to your branch. That's what that thing does. Good. That's what I wanted to show. I hope that helps a little bit more in terms of contributing to open source. Let me quickly stop sharing because I don't see anything. Here, cool. Are there any questions?
Yes, Leandro, this is something, I really think it's really helpful. First I would say, the testing, I saw the first time you just did the code change and you push it into the Git, the repository without testing locally. I guess there's something in the repository, it can automatically, check your stuff. That's why it showed some warning. Then the second time you did some local test, use the PyTest, right? So I guess PyTest will only check maybe grammar or syntax. It doesn't check the functionality. Suppose you have done a really complicated change, impacting the functionality, are you gonna test locally or test in the repository? And if you need to test locally, do you have the computing power, like in case you need a GPU or whatever?
Yeah, so the PyTests, they actually do test functionality. They don't, the make style and make quality, they do some like syntax things where it's like replace single quotes with double quotes and so on. But the PyTests, they test functionality, and they're the same thing that runs remotely on the repository. So it's just a useful thing to do locally because you can iterate quicker. You don't have to push to a repository to see if it works. You can do it locally, and you can even do it more fine-grained. You can just, if one test fails, you can just test that one again and again until you fixed like what broke it, essentially. And in terms of computing, usually these tests, they're not training models or something like that. They just test if functionally the thing is still doing the same thing as it was doing before. Sometimes it does like a single forward pass or a single backward pass on like a tiny model, but it doesn't like take a 100 billion parameter model and trains it or something like that. So these tests are supposed to be very lightweight, and they should run like in a couple of minutes, even on a local machine. I'm afraid we're kind of running out of time. So I want to say like a few organizational things, and you can, if you have more questions about that last bit about open source, you can just post it in Slack, not Slack, in Discord, and I can try to answer your questions. On the organization side, we're going to do the same thing we did last week. We're going to make we're going to ask which chapters you want to see next and want to discuss next. And I think it would be really nice, like Siddharth showed today, like giving like a nice summary. If someone would like to do that, that would be super cool. As I said last time, if you do that, we can either give you a book if you want one, if you don't have one. If you want like a hard copy, Lewis and I can sign it if that's something you want. Or we can give you like a voucher from the Hugging Face story, so you can buy like a hat or something. That's one thing. And the other thing is, like, I think it would be cool to, if you are interested in contributing to open source, if you would try to do it. There are a lot of like good first issues on transformers or evaluate or a lot of open source libraries that also doesn't need to be in the Hugging Face ecosystem. And you can use like the Discord channel to look for help if you want to do something. If you, maybe there's like a few people who want to open a PR, maybe you want to work on it together. If you need some help or guidance, you can ask me or Lewis or some other people. Maybe you opened some PRs before, and we can try to help you. So that's one thing. And one thing that we can also do, we can give the same kind of prizes to like the coolest PR or coolest thing you did with the chapter. So we're going to do it like for both. If you want to do something with the book, maybe this week is not ideal because it was mostly theoretical, but maybe next week when we train a model on something and you want to build a cool demo, or you want to train a model on another data set or something like that, we can also do something in that direction. Cool. So thanks a lot for showing up and sticking around, even though we went a little bit over time. Hope you have a nice day, nice evening, and see you in 2 weeks. Bye, everyone.
Bye. Thanks.
Bye, everyone.
Thanks.
Thank you.